So let's see how we apply the potential flow theory to doublets. Now, before we move on, just want to summarize a few things. So in the case that I can have a line with a bunch of singularities, these are singularities. Um, Consider axisymmetric body. Remember, axisymmetric body is one that I can rotate this about this. It's a two-dimensional problem, but really a three. And I can have a combination of sources and sinks. And what happens is I can adjust the shape. I can adjust the shape of this body. I can adjust what by just adjusting the strength of my source and my sink. And they are close if the summation of all my strength, okay, all my source strengths is equal to 0. Then it's a closed loop, and we have an open shape. Otherwise, so this is a closed loop, okay, something like this. However, we could have, let's say, a flat line, right? A flat line with all the sources. In this such a case, then Qi will not be equal to 0. So here, in this particular topic, what we're going to do is we're going to assume that the distance between this point and this point and this point is completely 0. So they are actually coincide, they're in the same point. So we're going to take delta 0. But just to separate the idea that I'm going to have a sink and a source, I will put a minus delta and a plus delta. But think about your delta being very, very, very small, okay? And we work in the polar coordinates or cylindrical coordinates, where this is the distance x and this is the distance r. Okay, if this is the angle theta, then you can immediately see that x is equal to big R cosine of theta. Your small r is equal to big R sine of theta. Sine of theta. Okay. Basically, the idea behind this is if I take just the uniform flow and the doublet, I add them up, what I'm really doing is I'm analyzing what happens to a circle or a cylinder if you want in 3 dimensions. Okay, so or a sphere, right? So if it's an axisymmetric problem, then this is a sphere and not a cylinder. So in this case, this is what we want to analyze, and we're going to do that by taking the uniform flow plus the doublet, and we will study what happens to it. Okay, so to do that, I'm going to go and take everything we learned previously in spherical coordinates, and you can show that what you end up having here, where this is R1, this is R2, R1 to the sink, R2 goes to the source. Then if that's the case, then it's 1 over R2 minus R1, and you end up with this expression, where R1 is equal to this expression right here. Okay, again, it comes from R1. If you do the math between x and you do all the geometry, you will be able to show that this is what you get. Now, you want your delta to be far smaller, very, very tiny. It's almost 0. Then you can say your R1 is actually all of this reduces to this, or rewriting this, taking R out, this is equal to this expression. Now, I can further go and use the binomial expansion function, where for small delta, being this expression very, very small, so this expression would apply. So this will equal to this. And by simplifying, you can say this is equal to this. And if you know that, remember, x is equal to r cosine of theta, replacing the value of x there, then you end up being r minus delta cosine of theta. Likewise, you can show that R2 is approximately equal to this. So if I take the subtraction and the multiplication of these two, then what you can show is that your phi is actually equal to this nice expression. Okay. Now, typically we use mu to represent the strength of the doublet, and the strength of the doublet would be, if you look at here, right, is 2 times delta Q. Okay, that is the strength of your doublet, and it's a constant. So basically, your doublet is equal to this, and it produces your potential. And your potential is going to produce a bunch of circles that actually pass through the center. That's what we are doing. Okay. Um, so given by that, let's see what the equations are. Then from here, we can say that UR is equal to partial of phi respect to r minus mu cosine of theta 2 pi r cubed, and that will equal to 1 over r squared sine of theta partial of psi partial of theta. Okay, so this comes from this equation right here. Take the derivative respect to r, and then I equate this expression to this expression so I can find the value of psi. Okay, so if I solve for psi, I integrate respect to psi of theta, you can find that the expression becomes minus sine squared of theta 4 times pi r plus fr. Okay, so, and if I want to find u theta, if I go to u theta now, have 1 over r partial of phi respect to theta. Again, go back to this expression and take the derivative with respect to theta. Then I end up with mu sine of theta 4 pi r cubed. And note that that's equal to minus r sine of theta. This is simply in your cylindrical coordinate system. So from here, I can equate these two and solve for psi. And your psi is equal to minus mu sine squared 4 pi r plus f of theta. Okay, so now if you go to here, you can compare these two, right? And you can immediately show that this is a function of theta, but then you can say, you know, I got a function of r and theta. They're kind of these identical expressions. So since they're identical, we can deduce that these functions will be zero. But we will find them as we follow in the next topic. So really, all we have done is we have found what the value of the doublet is. So let's put it all together now. We remember the goal here was always to solve this problem, not this problem. Okay. So if I do that, then I'm going to save some time here because we have done this several times now. Okay. So if I want to find u, I just take the derivative with respect to r, and you can show that this is what you're going to get. And then use derivative with respect to theta, then this is what you will get. Okay. Then if I want to find the maximum possible r, so if I take ur equal to 0, I can solve for r cubed is equal to mu times this, and from here I can solve for r. So this would be the maximum radius your doublet can have. Okay, that is going to determine the radius of the doublet. Okay, so then so if I want to find what happens here, know that u of the the surface of radius constant, right? If this is radius, is r, is actually a sphere. And the component r will be 0 perpendicular to the sphere. Okay, so this is my velocity potential, and we have seen this before. If you remember one of your previous homeworks, actually we had this expression. You just didn't know where it came from, so now you do. And then if I want the streamlines, well, then you know how to find the streamlines, right? The same way we did here. You're going to equate, you make sure that this expression is equal to this expression. You make sure this expression is equal to this expression, then you solve for psi. And if I do that, then you can find this is expression, and you find this plus constant. Okay? To find the constant, you evaluate everything. What happens when you're evaluating everything at r equal to 0, and you're evaluating at theta equal to pi, let's say, and the function has to be 0. So when I put the 0 there, I get identical to 0, so my constant is 0. So if I move on now, you can see that your psi is 0 here, psi is 0 there, will be 0 on the surface itself. That's how we define psi. Now, if I want to know, so this is the points here, right? So theta is equal to 0 at this point and this point. Is equal to, at the value right here will be theta equal to this value. So what I do is I find my theta, and I solve and I evaluate this, and I find this answer. Okay, so oh yes, I want you to, the negative time really means that we chose the counterclockwise flow. But if it was positive, then it means they just go in the other way, the other direction. So if I wanted to find the drag on a sphere, remember, then I need to go back to my Bernoulli's equation. So that's how I can find my pressure. Anytime I want to find my drag, or I want to find my lift, I need my pressure. Okay, and we derived this before, so this is the general expression that we have. And then if I take a small strip here, that strip, as we did before, and find all the pressure distribution and do all the geometry, you can show that this is the final expression that you get. And then if I evaluate this expression now, it goes from 0 to pi, and so I evaluate this expression. You can show that you get this equal to this. This is a minus sign. So then your drag expression is this. Okay, so now here, at P, I need to evaluate, plug in this value. Okay, but before I do that, let's see what happens to your value of u theta when r is equal to a. Remember, you are trying to find the drag of the body on the surface, right? Not inside the surface, on the surface. So on the surface, r is equal to a. So if I did that, r equal to a, you find the expression of u theta is equal to this. So I can plug this value in there. And then if you do this, you do the whole expression, you find that your drag is equal to 0. Actually, spheres and cylinders are the best. You want a system that gives you the best optimum drag, best optimum lift with the minimum drag. It's a sphere and a lift and the cylinder. That's the whole idea. That's the perfect structure, and that's the perfect and the dream structure that we can have. So next we're going to do some examples and see how all this actually works together.